Right, transposes, crazy things, and this is a little video extra about the kind of amazing result that AB, product of AB, any two matrices that we can do this properly with. So we have an M by R and an R by N. So these guys match up and they make an M by N. If we take that transpose, then we can also get there with taking the transpose of B, so we swap the order, and then the transpose of A and multiplying them together. So we're going to take the transpose here, so this becomes an N by R and we have an R by M, so they match up again, the R's are in the middle, and we get an M by M, which is the flip of what this is. So it's the right shape, and we argued in class this one way. I'm going to give you three ways to think about why this is true. Yeah, three ways of looking at this particular blackbird, not 21. So here's just a sort of representative A and B, and I've given them some shapes that can help when we take the transpose of them, but these are arbitrary of any size. M by R, and then R by N, so R rows here, R columns, they match. And let's look at what happens when we take the normal matrix multiplication, the ith row, we're going to have the dot product with the jth column, and that will be the ijth entry of the product AB. Right, this is how it works. When we do multiplication, so we take the ith row, jth column, dot product, that's the ijth entry of A times B. Fine. Let's do one more little step here. That is, by definition of the transpose, it's the ji entry, so we'll swap I and j. So if this was 2 and 7, this is 7 and 2, of the transpose of A times B. Just the definition of the transpose. We're going to flip it. So that's there. And if we line up B transpose and A transpose, we're going to swap the order of these and then take the transpose of them. So B is going to be flipped to here, A is going to be flipped to here, so it's tall here, it's wide here. And then we'll take those same, so we'll take this row in A, which is now a column in A transpose, and the column in B, which is now a row over here in B transpose. So they're the same pair, and that dot product has to match up with that dot product. It's just now we've rotated the order, or flipped the order. So the jth row of B transpose and the ith column of A transpose, it's the same number, and it is the ji entry, right? It's ji entry of B transpose A transpose. These are the same numbers, so the things we've gotten to here must be the same, and because we have, this is the ji entry and this is the ji entry of B transpose A transpose and AB transpose, then everything is all sorted out, and we have our result. AB transpose is B transpose A transpose. So let's look at a couple of other ways. So we'll take away the picture, we'll just do it just with algebra. So AB transpose IJ, right? So let's take this character. First thing we can do, the definition of the transpose is that is the ji entry of A times B. We'll just flip this. And then we'll introduce the definition of matrix multiplication. So we're going to sum from k equals 1 to r of the jth row and the of A and the ith column of B. So that's all very good. So let's now sneakily put in the transpose, and we can always do this. It's no problem. So if we want to write in the A transpose, then that same value is in the kj location. So we have to swap these guys. B transpose, it's the ik location, and this is still the sum from k equals 1 to r. Now this looks like a normal matrix multiplication story if we change the order. And so let's do that, and I'll explain what I mean. K equals 1 to r, so I'm going to put the B. This is so exciting, people, so exciting. This is pretty cool, actually. This is fantastic. A transpose, matrices are better than most of us. They match up. K equals 1 to r. K's are here. So this is the ij entry of this blob times this blob, and which is B transpose, A transpose, ij. So I'm giving you different ways to do this. This might be your jam up here. Might be this one. Let's do some madness with some advanced matrix wrangling. It's good to think of multiplication in these kind of powerful ways. In general, we have these two rectangles multiplying each other. They have to match on the inner dimensions. AB transpose, let's start off with that, and let's mess around with this thing and see what we end up with. So, on a previous video we talked about this, so we can write this as A, and then separate all the columns of B, and then A comes in and multiplies, if you think about how the dot product works, in the definition, it's really A times B, which is now a vector, because this is a matrix times vector, gives you a vector. That's the first column. Then A times B star 2, so this is A times the second column of B, A times the nth column of B. So, that's nice, they're all stacked up. And then we're going to take the transpose of that. So let's take the transpose. We have to do a sneaky thing in here. Let's do it. So we'll take the transpose, so this is a vector, it's A, B star 1, transpose is going to be across the top. We're going to put the A, B star 2, right, so A times the second column of B, that's going to be here. All these guys are now stacked, so they've gone from arranged as columns to stacked this way. So sum of columns of A. So what's going on here? What does this do? This is our column picture type of thing. We'll become more and more familiar with this. This is A, it's a bunch of columns, and B says, if we multiply it by vector B, it says, all right, I want all of those columns, think of them as a musical instruments, and B is the volume, so I want to add them up, give them these weights, stack them together. Now this transpose gives us something else to do, because we can say, well, all right, let's turn A around, we'll make it into rows, and we'll have to change B into a row vector, so it's B. This B star 1 is now going to be a row vector. And now we're going to add up A transpose's rows, which were A's columns. And we'll do that for all of these vectors here. And then this A transpose is sitting here, and we can extrude it out to the right. This is we're sort of doing the opposite of what we did here. And we have a stack of these, what were the column vectors of B, but they've been transposed. Now we see B transposes here. So this one is sneakier, a little more power in here in some ways, but we get B transpose, A transpose. That's what we wanted. Lots of goodness. Last little thing I'll say is that this generalizes. You can see how this will work, but let's say we had A1, A2, up to AN transpose, then the same thing with inverses. So AN transpose, we just put them back to front, all the way back to A1 transpose. Okay, so that's so we reverse the order, and it generalizes to larger numbers. All right, that's good.